Hi everyone. Next we are going to discuss about Maxwell's first equation. So what is the Maxwell first equation? Gauss law is the Maxwell first equation. So we know that the integral form of the Maxwell first equation is psi is equal to q, that is equal closed surface integral of d bar dot ds bar, where q is equal volume integral of rho v into dv. So rho v is the volume charge density. So this equation is called as Maxwell's first equation. That is integral form of the Maxwell first equation. So next, determine differential form or point form of the Maxwell first equation. How to calculate the differential form of the Maxwell first equation using divergence theorem. What is the statement of the divergence theorem? Closed surface integral is equal to open volume integral. So d bar is the electric flux density, which is the vector quantity. So using divergence theorem, the closed surface integral of d bar dot ds bar is equal open volume integral of del dot d bar into dv. So using divergence theorem, closed surface integral of d bar dot ds bar is equal open volume integral of del dot d bar into dv. So using integral form of the Maxwell equation, closed surface integral of d bar dot ds bar is equal open volume integral of rho v into dv. Substitute closed surface integral of d bar dot ds bar is equal open volume integral of rho v into dv. In this equation, we get LHS term is integral rho v dv is equal RHS term is integral del dot d bar into dv. On both sides, cancel the volume integral, we get del dot d bar is equal to rho v. So this is the equation of differential form of Maxwell first equation. Rho v is the volume charge density, d bar is the electric flux density. So we know that the relationship between electric field intensity and electric flux density is d bar is equal epsilon naught into E bar. Therefore, del dot E bar is equal rho v by epsilon naught. So that is differential form or point form of the first Maxwell equation. Next, we are going to discuss about applications of Gauss law. And the first application is determine electric flux density due to the point charge. Suppose a point charge Q is located at the origin. At the origin, point charge Q is located. So consider differential surface ds on the surface. At that point P, the direction of the electric flux density is always radially outward direction or normal to the surface. And the differential vector surface area ds bar is also moving the same direction. Okay. So we know that the vector form of the electric flux density is d bar is equal dr into ar bar plus d theta into a theta bar plus d pi into a pi bar. In spherical coordinate system, the vector form of the electric flux density d bar is equal dr into ar bar plus d theta into a theta bar plus d pi into a pi bar, where dr, d theta, d pi are the magnitudes of the electric flux density. AR bar, A theta bar and A pi bar are the unit vectors in R direction, theta direction and pi direction. So now here the electric flux density is varying only R direction, that is radial direction. It is moving radially outward direction. It is not varying theta and pi direction. So because of that, in vector form, d bar is equal to dr into r bar. D bar is equal dr into ar bar, where ar bar is the unit vector in the direction normal to the surface. In spherical coordinate system, the differential surface area ds bar is equal r square sin theta d theta d phi into ar bar. So now determine d bar dot ds bar value. So d bar is d bar is dr into r bar and ds bar is r square sin theta d theta d pi r bar. Dot product of same unit vectors is 1. That is r bar dot r bar is 1. So that is equal d bar dot ds bar is equal dr into r square sin theta d theta d pi. Taking closed surface integral on both sides, we have closed surface integral of d bar dot ds bar is equal closed surface integral of RHS term. So LHS term is charge enclosed by the surface, that is q, is equal dr into r square integral. In spherical coordinate system, theta is varies from 0 to pi and pi is varies from 0 to 2 pi. Integral theta is equal to 0 to pi sin theta d theta. Integral pi is equal to 0 to 2 pi 1 d pi. Integral sin theta is cos theta minus cos theta over 0 to pi. Integral 1 d pi is pi over 0 to 2 pi. After substituting values of theta and pi, we get RHS term is dr into r square 4 pi. So from that equation, the component of dr is equal q by 4 pi. Substitute dr value into vector form of the electric flux density. Now here, the electric flux density is varying radially outward direction, that is r bar direction. So what is the vector form of the electric flux density along r direction? D bar is equal dr into r bar. Substitute dr value into that equation, we get the electric flux density d bar is equal q by 4 pi r square into r bar. So what is the relationship between electric field intensity and electric flux density? D bar is equal epsilon naught into E bar and E bar is equal D bar by epsilon naught. So that is equal electric field intensity E bar is equal Q by 4 pi epsilon naught R square into AR bar. So this is the equation of electric field intensity or electric flux density at point P due to the point charge Q is located at the origin. Point charge Q is located at origin.